Greetings of the day, dear students. In this video, we are going to discuss about different losses and efficiency in a DC machine, and we will discuss its classification and also the formulas related to the losses, and also we will discuss some examples how to calculate the different losses and efficiency for a given DC machine based upon the data given, right? If we observe for any given system, don't think that the entire input power given will be appear as output in the process of the conversion from one form of energy to the another. Okay, the whatever the input energy given, it will not appear entire energy as output. Definitely there will be some amount of losses. So obviously what happens is our output, for example, if you are having a system like this, whatever might be the system, for example, observe, you have given some input power, right? And the amount of output power we get will be equals to the input power minus some amount of losses that occurs here, right? After subtracting the losses from the input, that will be the available output. So obviously if you want to deal with the efficiency, what happens is our efficiency will be the output power output by input, right? Now because of these losses, what happens is the efficiencies of the machines also will reduce. The efficiency of the machines also will be reduced. More number of losses, very less will be the efficiency of the machine. So the losses have a very important role to decide the efficiency of the machine. With respect to the DC machines, what happens is this is the major classification. As we have discussed earlier, with respect to the principle of operations of DC machine, we are having armature winding, field winding, and also we are having some rotating parts. Because of all these things, there will be some amount of losses. Now because of these losses, what happens is there will be the rise in the temperature of the machine, and also it will lower the efficiency of the machine. Dear students, please observe, this is the classification. We are having copper losses and iron losses, or magnetic or core losses, and mechanical losses. Again, this copper losses is divided into armature copper loss, shunt field copper loss, and series field copper loss. And iron losses or magnetic or core losses is due to the is again further divided into hysteresis loss and eddy current loss. Mechanical losses, we are having friction loss and windage losses. If we observe these copper losses are mainly due to the flow of current in the armature winding or shunt field winding or series field winding. And the magnitude of loss, how much amount of power is lost, is given by I square R, the amount of current flowing in that particular element and the resistance of that particular element. For example, if it is armature, if the current flowing through the armature is IA and the resistance of the armature winding is RA, then IA square RA, amount of power will be lost in the form of heat in armature. Like that we have to understand. Similarly, in the shunt field winding, the winding which is made up of some conducting material, obviously it will have some resistance R. Because of the resistance offered by the material and the current flowing in the material, I square R amount of power will be wasted in the form of loss. If in the shunt field winding, if the current flowing is ISH and the resistance of the shunt field is RSH, then ISH square RSH amount of power is lost in the form of heat. Clear? Similarly, in the series field winding, if the current flowing is ISC and the resistance of the field winding is RSC, then ISC square RSC amount of power is lost. And the hysteresis loss is given by eta B max power 1.6 into F into B. And eddy current loss is given by some constant K times B max square F square T square V. Clear? So these copper losses are mainly due to the resistance of the windings and also due to the current flow, and the hysteresis loss and eddy current losses we will discuss now. And these mechanical losses, because of the rotating parts in the DC machine, we used to have some friction between the rotating parts and the bearings and the brushes, and because of the air gap we used to have some windage losses, right? And so these are the main classification of the different losses in a DC machine. Right, now let me see about the copper loss. These loss occurs mainly due to the, as we have discussed earlier, mainly due to the current flowing in various windings. In our DC machines, if you observe, we are having armature winding, armature, shunt field winding, series field winding, like that, right? Armature copper loss IS square RA, shunt field copper loss ISH square RSH, and series field copper loss ISC square RSC, ISC square RSC. Now what about this iron losses, or sometimes core losses, or magnetic losses? These are mainly due to the rotation of what? Because of the rotation of the armature, okay, in the presence of the magnetic field, because of the field winding and excitation given to the field winding, we are getting the magnetic field, and as this rotor or armature conductors are rotating in the presence of this magnetic field, there will be some amount of losses, mainly due to the this armature will be rotating with some speed n rpm, and the conductors are placed in those slots, and they will be subjected to the magnetic reversal, there will be subjected to the magnetic field reversal because of the rotation of the conductors armature. Those conductors will be subjected to what? Those magnetic field winding is fixed, north pole, south pole, those are fixed, but these conductors are rotating in the presence of the field. Because of that, those conductors will be subjected to the magnetic reversal. Because of that, what happens is some loss will occur, some losses will occur. So mainly due to the magnetic field reversal of the armature conductors, and as it passes under the successive poles. For example, here, if P is the number of poles, as you have discussed, if you recollect the formula, how much EMF is back EMF is induced or generated voltage EG is given by phi Z N P by 60A, right? Now the frequency of the reversal of the frequency of the magnetic reversal F is given by Pn by 120. This is important. The frequency of magnetic reversal, whether it is at 50 Hz or 60 Hz, right? That is decided, or at some 25 Hz, right? That is this that will depend upon the Pn by 120. P indicates the number of poles, N indicates the speed, right? Based on that we can decide the magnetic reversal frequency. Now hysteresis loss is given by the formula WH, W power in watts, expressed in watt, WH equals to eta B max power 1.6 into F into V. In this formula, eta indicates the Steinmetz hysteresis coefficient. Bmax is the maximum flux density in armature winding. F indicates the frequency of magnetic reversal, and V indicates the volume of armature in meter cube. One interesting point you can observe here is the hysteresis loss is proportional to the frequency. If the frequency of magnetic reversal is more, then there will be more amount of hysteresis loss. If the frequency of the magnetic reversal is low, there will be less amount of hysteresis loss. Clear? Similarly, if the value of this eta is low, if you have selected a material in such a way that if the coefficient, the hysteresis coefficient of that particular material is low, then you can reduce the hysteresis loss. If somebody asks you how you can minimize the hysteresis loss, why? Because if the losses are low, the output will be high. If the output is high, what will happen? What is the formula for efficiency? Output by input. So obviously if your losses are less, then output will be high, then efficiency will be high. So definitely after understanding the losses, right, we should be in a position to know how to minimize the losses, especially in hysteresis loss. What you can do is you can select a material which is having very low eta value. Such kind of one material is silicon steel. Silicon steel will have hysteresis coefficient very low value of hysteresis coefficient you can have for silicon steel. So that is the reason, if the core is made up of such kind of materials, then you can minimize the hysteresis loss. If the core is made up of silicon steel material, then hysteresis losses will be less. Clear? Now next is the eddy current loss. Eddy current. What happens is, so far we are saying that in the presence of the magnetic field, if armature conductors cuts the magnetic flux, right, some voltage will be induced in the conductors. But at the same time, these conductors are placed in the slots. Those slots is nothing but the core. That core is also made up of some conducting material. Now, because of this magnetic field, some amount of voltage will also be induced in the armature core. Very important. Because of the voltage induced in the armature core, what happens is some current will be circulating in the armature core, not only in the slots, not only in the conductors placed in the slots of the armature, but also on the outer surface of the armature core also. There is a there is a possibility for the circulating currents to be produced. Very important. This is not due to the EMF induced in the conductors. This is due to the some voltage induced in the core, armature core. In the armature core, what we are having, armature winding we are having. Actually, if the more amount of voltage is induced in the conductors, that is good, no problem. But if the voltage is getting induced in the core surface, then it leads to the problem. Why? Because of the induced voltage, some currents will be flowing, circulating in the core. Because of these currents, I square amount of power will be lost. I square R amount of power will be lost. Now, if you can reduce the resistance of core, if you can increase the resistance of the core, if the overall resistance of the core material is increased, then it offers high resistance path for the eddy currents to flow. Then you can minimize the eddy current losses. So one way to minimize the eddy current losses is, instead of using a solid thick block of armature core, that core is made up of some thin laminated core. The shape wise it looks same, but instead of making that armature core with a single solid block, you make it with the help of some thin laminations, and those laminations are to be insulated from each other using the varnish material. I repeat again, simply to say, the eddy current losses are mainly due to the voltage induced in the armature core. This induced voltage will produce the circulating currents in the armature core. If you want to minimize, use the laminated core, right? So simple. For that sake, those are insulated from each other using the varnish insulating material. and the loss is given by the formula, eddy current loss is given by the formula K B max square F square T square V. In this entire formula, K is a constant depending upon the resistance of the core, B max maximum flux density in Weber per meter square, F frequency of magnetic reversal in H, sorry, thickness of lamination in meter, and V volume of core in meter cube, volume of core in meter cube. These things are important, dear students. Okay, so far, let me complete this one also. Laminating you laminating a core will increase the core resistance. Because of the increase in the resistance, it offers high resistance path to the eddy currents, so I square R loss will be reduced, eddy current will be minimized. So far, just once recollect: eddy current loss, hysteresis loss, copper losses. All these losses we have discussed so far: armature, shunt field, series field. Hysteresis loss due to the magnetic reversal of the armature. Conductors placed in the armature will be exposed to the magnetic reversal, and eddy current losses because of the voltage induced in the armature core. Simple, right? And the last one is the mechanical losses, friction and windage losses, right? Clear up to here, right? Hysteresis loss to be minimized by using silicon steel. Eddy current loss, how we can minimize? By using laminated core. You can minimize the eddy current loss. Eddy current loss, if you observe the formula, proportional to the square of the frequency. So, frequency square. Hysteresis loss is proportional to the only frequency of the magnetic reversal. F power 1 only is there. Eddy current loss, square of the frequency. If the frequency of magnetic reversal is more, eddy current losses will be more, right? Yeah. Now mechanical losses, you can easily understand this. Because of the rotating parts in the DC machines, right? Stator is fixed, rotor is rotating, and rotor nothing but the armature slots. It will place on the shaft, and it will be touching the slip rings, brushes, bearings. All those setup will be there. So obviously, when some rotating parts are there, there will be some amount of friction, right? And bearing friction or some brush friction. Because of that, some losses will occur. And because of the air gap, some gap provided between the stator and rotor, some small amount of gap will be provided, right? And also because of this rotation, some air friction, we will have the windage losses, right? So most of the times these losses will depend upon the speed of the machine. These losses will depend upon the speed of the machine, and for a given speed they are particularly constant, they will be constant, right? And stray losses, sometimes what happens is iron losses plus mechanical losses together called as stray losses. Iron losses plus mechanical losses together called as stray losses. In some textbooks you can observe the classification like this also. They will instead of saying, if you observe, let me show you the first slide, they will classify like this: constant losses and variable losses. Constant losses, variable losses. But observe our first slide. This is the classification we have taken. At last all the losses will be same, but the way of classification is something different. In this entire setup, some losses will be constant irrespective of the load, depending upon the load on the machine, whether you have applied half load, full load, or 1/4 load on the machine, depending upon the load, right? If it is generator, the amount of current generated by the machine will change. With also motor, depending upon the load, the amount of current drawn by the machine will change, right? So based on all those factors, depending upon the load, some losses will be changing, but whereas some losses will be constant irrespective of the load on the machine. If it is generator, we will apply the electrical load. If it is motor something, we will apply the mechanical load on motor. On motor output, we will apply some any some rotating mechanism or something we will expect, right? So here iron losses, under constant losses, iron, mechanical and shunt field losses are constant in a given machine. But whereas series field winding and armature copper losses are variable. Series field copper losses and armature copper losses are variable losses. Iron, mechanical and shunt field losses are constant losses. Constant loss. This is also okay. This is also one type of classification, right? Now, so this is all about the losses. Coming to the efficiency of the machine. Yeah. Now coming to the power stages in DC generator, different power stages, right? As you are already familiar, it converts the mechanical energy into electrical energy, and we are having different parts, right? At last, our target is to find out the efficiency, right? And just we have previously told that efficiency something, for example input power is there will be some amount of losses and we will get the output. Efficiency is given by output power by input power. Now whatever output we are getting is nothing but the input power given minus losses whole divided by input. This is how we can express efficiency in terms of input. This is one way. Or our input or your input is nothing but the amount of power that is wasted or loss plus the output available. So input can also be written as output plus losses. Input can also be written as output plus losses, or output can also be written as input minus losses. All these three are okay. Depending upon the problems data given, you can use any of these three formulas to calculate the efficiency. That is the reason why once if you know the input and if you know the losses, you can calculate the efficiency. Or if you know the output and if you know the losses, you can calculate the efficiency, right? Losses already we have seen how to calculate all those losses, right? Now in this efficiency, you can observe here, understand, mechanical input power is given. Let this block be the A block. Now whatever this mechanical power input is given is not going to appear at the at the armature the power developed is EGIA, right? Out of this much mechanical input power, because of the iron and friction losses, that part will get subtracted. That part is subtracted from mechanical input power, these iron and friction losses. Now whatever the power is developed, some EGIA, out of this copper losses will be subtracted, all the copper losses, and at last the power available is only V into I, electrical power output, V into I. Clear? So stage A minus iron or friction losses will give you stage B. Stage B minus copper losses will give you stage C. Clear? Now if you are asked, if you are asked to calculate the mechanical efficiency, B by A, B B divided by A will give you the mechanical efficiency. But what is B? Observe, that is nothing but the power generated at armature. How much power will be generated at the armature? Armature, the power generate voltage induced is Eg, or generated voltage is Eg. Current developed Ia. So Eg times Ia, amount of power. As you know the formula for power, power P equals to VI, voltage into current. Generated voltage is Eg. Current delivered by the armature Ia. Mechanical power supplied. Mechanical power supplied. Similarly, electrical efficiency eta E is given by C by B ratio C. But what is C? Power available at load. Power available at load divided by power generated at armature. But what is the amount of power available at the load? The current drawn by the load, the voltage across the load, terminal voltage, current drawn by the load, we have seen in DC machines classification, if you recollect. Right? So dear students, don't directly watch this video. Before watching this video, please complete the basics of DC machines classifications, right? Different types of DC machines and different terminology. What do you mean by V, IG, EG, IA, RSH, RSC? Are you getting? All those terminology are important, right? Yeah. Now V into I divided by EG, IA. V is the terminal voltage, I is the current drawn by the load. So V into I divided by EG, IA will give you the electrical efficiency. Now overall efficiency or commercial efficiency, eta C divided by A. How do you understand that? Power available at load divided by mechanical power supplied. Mechanical power supplied. So in the problems, if nothing is specified in a given problem, he has not stated anything. If he has not specified anything, he simply asked you to calculate the efficiency. Then at that moment, dear students, please don't get confused. You simply calculate the commercial efficiency. You simply calculate the commercial efficiency. If nothing is specified in the problem, which efficiency you want to calculate, then by default, please calculate the overall efficiency. Clear? This point is important. Please remember. If problems are given for you in your exam, right? Yeah. Now, these are the losses. Just already we have completed. Input minus losses will be our output. Or losses plus output will be our input. Now, what is the power generated output power is VI. But what about input? Observe here, nothing but output plus losses. Output is VI. What about losses? I am dividing it into two parts, variable loss and constant loss. Constant losses are fixed irrespective of the load on the machine. Variable losses will change with respect to load, right? Now ia square ra, constant losses I am denoting with letter WC, constant losses WC VI. But what about armature current? For a shunt machine, if you observe, this is a shunt field winding, this is the armature, and this is the generated current IA equal to current drawn by the load I plus some amount of current goes to the field winding ISH. If you recollect, this is the generator, armature winding, armature resistance, shunt field resistance you will have. This is the armature shunt field resistance RSH. This is the voltage generated EG at armature, right? IA, if you apply KCL, IA equals to how much? This is the current I plus ISH, that is what you have written here, I plus ISH whole square into RA plus omega C. But if you observe, with respect to compare to the IA, ISH will be very small. ISH is very small, so you can neglect the ISH value. Magnitude of ISH will be small, so if you neglect the ISH, if then what happens? IA is directly equals to armature current will be equals to the load current I. So output by input VI divided by VI plus I square RA plus omega C. Now if you further simplify that, 1 divided by 1 plus I RA by V plus omega C by VI. Just we have taken out VI common, right? Now for the efficiency is to be maximum. For example, somewhere you have seen some Z equals to X by Y. If Y is minimum, Y is less, Z value will be very high. So denominator, if efficiency is to be maximum, this denominator is to be minimum. The denominator value is to be minimum. If in order that to be minimum, mathematically we have to take the derivative of that first derivative and make it equal to 0. Then you will get the condition for maximum or minimum values. First derivative, take the first derivative of that denominator part and make it equal to 0. So derivative of that with respect to what? With respect to the change in the current, with respect to the change in current di. So derivative of I RA by V plus omega C by VI equals to is to be made equal to 0, is to be made equal to 0. Then we will get the condition for efficiency, right? Yeah. So RA by V is taken out common, derivative of current with respect to current plus omega C by V is taken out common, derivative of 1 by X with respect to X, right? Derivative of 1 by X with respect to X. So RA by V, derivative of X with respect to X is 1, right? And derivative of X power minus 1, derivative of X power minus 1 with respect to dx, how much you will get? Minus 1 into X power minus 2. This is nothing but minus 1 by X square. That is what you have written here. Minus 1 divided by I square. So if you further simplify, RA by V minus omega C by Vi square is made equal to 0. RA by V equals to omega C by Vi square. So if you observe, I square RA equals to omega C. Very important. What happens? But what about I square RA? I square RA is a variable loss. Omega C is a constant loss. So if variable loss is equal to the constant loss, then the efficiency is maximum. Very important. Very important. If variable loss is equal to the constant loss, then the efficiency of the machine will be maximum, right? So this is the condition. How we got that? Simply by writing the efficiency formula, output power, and expressing input in terms of output, and neglecting shunt current, and making the denominator derivative, first derivative of the denominator equals to 0. You will get the condition. Of course, most of the students will not have this condition for maximum efficiency in their syllabus, but for your understanding sake, quickly I have explained the condition for maximum efficiency. Most of you electrical people will have, electrical engineering students, definitely they have to know the condition for maximum efficiency. But I have observed so many syllabuses, most of you may not have this condition for maximum efficiency in your syllabus as per your academic syllabus, but just you can observe the derivation, right? Yeah. So at that time the current is given by root omega C by, if you observe the current I equals to root omega C by RA. If you able to draw, if you are able to design, if you are able to apply load such a way that if it draws current I equals to root over omega C by RA, then at that time the efficiency will be maximum. Efficiency will be maximum, right? So this is what, dear students, all about the efficiency and maximum, sorry, efficiency and losses, efficiency and losses. Next we will discuss the some problems in the next video, right? I will discuss the problems, all the problems, exclusively all the problems in the next video. And this is the theory part up to here, right? uh, Power stages, mechanical loss, stray losses, eddy current losses, hysteresis losses, core losses. For 2 marks also it will be very helpful topic, right? Please prepare well this topic. These 2 marks or for essays also, problems also, these topics are important. Clear? Thank you.